Hey everybody, we're going to do section 5.4 today. This is our last section that we're going to be doing in this semester of Math 1101. We're going to talk about logarithms, and those can be scary maybe because it's new notation, but hopefully it will make it fun. There's a song I like to sing. Comes from a TV show from the 90s probably, called Ren and Stimpy. Probably don't know what that is, but anyway, there was a funny commercial that the characters from this show watched. It was supposed to be about a new toy called Log. It's just a log, right? Piece of wood. And here was the jingle. What rolls downstairs tumbles over in pairs. What rolls over your neighbor's dog. What fits on your back and it's great for a snack. It's log, log, log. It's log, it's log. It's big, it's heavy, it's wood. It's log, it's log. It's better than bad, it's good. Come on and get your log. You're gonna love it, log. It's Log by Blammo. Something like that, okay? Anyway, the point of what I'm trying to do there is to hopefully make these things a little less, daunting and more silly. But what are we really doing when we have a logarithmic function with base a? Well, the a is the same as the base of an exponential function. What a logarithm does, it undoes an exponential. It does the opposite order. In the same way that a square root undoes a square, or a square undoes a square root, log of a exponential, right, if the same base, they're going to cancel each other out. So I'm defining the symbol log base a of x, and this is not multiplication, right? It's log base a of x. It's a function as the thing that is the exponent that you raise a by in order to get x. So if you do log base a of a to the x, it's going to just give you x. Or by the same way, if you do log a to the log base a of x, that'll also be x. So we're going to use that. These functions are inverse operations of one another to hopefully solve equations later. But right off the bat, right, you can switch from logarithmic form to exponential form using this way here. Okay. Now I'll show you I'll talk about a little story that will help maybe make this easier to remember. But note that you can take the properties of exponents and change them into logarithmic form. So the logarithmic form is in red. So if a, whatever the base is, raised to the 0 is 1, then that means the log base a of 1 is always 0. And if you add powers of like base exponentials, that's like adding the logarithms, right, when you take the log of a product. So the log of a product is the sum of the logarithms, because that's like the in the exponential case, you take a to the u times a to the v, that's a to the u plus v. Okay? So like this here is like the u, right? That's the v. Anyway, you can do that for all the properties of exponents. And let's do a couple examples so you can see. First one here is like, what is the log base 10 of 1 over 1,000? Okay, well, one way that I can remember how to go from logarithmic to exponential form, think of the base here as being stuck under the log. So he's got the tunnel underneath, let's make this bigger. Okay, it's got the tunnel underneath here, the equal sign, but doesn't get far enough. So bumps his head on the y, right? So what's inside the parentheses is still on the other side of the equal sign, but the base is now raised to the exponent that was on the other side, right? So now we've changed log base 10 of 1 over 1,000 to 10 to the y equals 1 over 1,000. So we need to figure out what y is. Y equals -3 because 10 to the 3 is 1,000, but then you take a negative power, it's the reciprocal. So y is -3 since 10 to the -3 is 1 over 1,000, or the reciprocal of 10 to the 3. Right now, there are two special bases of exponential, but that means there are two special bases of logarithms. Okay, so the base 10 and the base e are special bases, and they have a special notation and name. So the log base 10 of x is usually written just log x, and this is called the common logarithm. On the other hand, log base e of x is usually denoted ln x, and that's called the natural logarithm. Okay, so there's a way to change every logarithm into one of these special bases. That's called the change of base formula. The only reason why we would want to do that is because your calculator has those buttons, log and ln, right? So if it were ln of 7, right, we could just type this into the calculator. This is not a whole number, right? ln of 7 is really log base e of 7. This is actually not a whole number, or it's not even rational. So the only way we can get decimal approximation is to type it in. Okay, but you can type it in. Now e is about 2.718. It's not equal to that, right? So it's not quite 3. So e to the 1 is smaller than 7, but e to the 2 is bigger than 7. So 1.95 is the approximate solution, okay, to that one. But if it's not in that form, say, I don't know, log base 5 of 125, right? Well, we could rewrite that in terms of log base e or log base 10, and I'll show you that in a minute. But this is going to be equal to 3 since 5 to the 3 is 125, right? Or log base a half. What is that? We think of log base a half of 16, that's going to be -4. And that's only because 1/2 to the -4 is 16. So, I mean, how would we check these using our calculator? We could use something called the change of base formula, and I will write it out in general later, but just in practice, what we're going to use is if you do the log base a of x, then you can rewrite that as ln of x divided by ln of a, or log of x over log of a, right? So let's try log base half of 16 and see if we get the right answer. Well, that would mean I do ln of 16, close the parentheses off, divided by ln of a half, and I get -4, okay? Now, how are logarithms useful? I said, right, we can use them to solve exponential equations, perhaps. Okay, so if you notice these data here is exponential growth, right? Every time I go from one to the next in the y values, I'm multiplying by 2, and the x values are going up by 1. So the average rates of change are doubling each time, well, they're increasing exponentially, right? So certainly I could find a function that models these data exactly using exponential regression. So we could do stat edit and number 0, which is the exponential regression. Start stat edit, enter the data into the lists, okay? But then stat calc 0 is the exponential regression that we could use to find the function that models these data exactly. What we would get is y is 3 times 2 to the x, because 3 is the coefficient, that's the y-intercept, and 2 is the base. The part B is asking to solve for x when 16 is equal to 3 times 2 to the x. Now, 16 is a whole number power of 2, so if this were just 16 equals 2 to the x, I would know the answer would be 4, because 2 to the 4th power is 16. But that's not what we're doing here, right? 16 divided by 3 is not a whole number power of 2, so we have to use logarithms to get the exact answer. You could find an approximate answer by graphing both sides, right? Solving the value, doing second trace 5 for the intersection to find the approximate place where they cross graphically. But I'm going to show you how to do it by hand. So we're going to first isolate the exponential part. So whatever that means. What that means is we need to get 2 to the x by itself. So I'm going to divide both sides by 3 to get 2 to the x by itself. And I'm going to leave some space because then I want to take logs of both sides. To undo the exponential. To do that, I can take log base 2 of both sides. The reason why I do log base 2 is because the base is 2, right? And so the log base 2 and the 2, they will cancel. And so what I'm left with is some number log base 2 of 16 divided by 3 is equal to x. And that's the answer. Okay, but if we use a change of base formula, I see, sorry, ln of 16 divided by 3 is the numerator divided by ln 2, the denominator, when I use the change of base formula. That says the answer is about 2.415. Okay. Now, how do we model logarithmic growth? Well, here, these data are not, they don't look like an exponential function. Look, this would be an exponential function. It looks like this. Okay, that's not what's happening here. If I were to find the graph of these data, it looks like this. Okay, so check this out. So stat edit, I already put the data in there. Okay, then I do second y equals, I want to turn on my stat plots, and then do zoom number 9 is zoom stat. Will automatically change my window. Look, there's what it looks like. It looks kind of like this motion here. That's not exponential. Okay, so we're going to try logarithmic function to estimate or to model these data. So if I go to stat, oh, and notice, right, even though the y values are doubling each time, roughly doubling, the x values are getting bigger and bigger. So this is very similar to what last week the governor of New York was saying was happening, that the number of patients was doubling, which is horrible, right? I mean, it goes to infinity, right? This graph will go to infinity. We don't want this to happen forever. But it was taking longer and longer for the doubling time to occur. And so that meant the rate of growth was getting less and less steep. So that was good news. But of course, we don't want corona patients to approach infinity. That will be bad. But here's kind of, we want that thing to get stretched out. Right? That's what the point of this is. Anyway, I do second, oops, what did I do? So first I went stat edit, and I enter the data, then I do stat calc. Number 9 is the ln regression, or natural log regression. So what do we do? So we stat edit, enter the data, then do stat calc number 9, which is ln reg. And the little r is close to 1 here, so it's a pretty good model. So y is about negative 5.778, let's say, plus 12.44 ln of x. So this is the answer to the first part. But the second part says, when will the number of patients be 100? And to do that, we need to solve a logarithmic equation. And just like before, right, first we need to isolate. But now we need to isolate the log. So to do that, I'm going to add 5.78 to both sides, and then divide by 12.44. Okay, but then I need to switch it to exponential form. Another way to do that, another way to think about that is I'm going to raise e to the power of both sides. Why e? Well, because that is the natural log's base, right? ln is base e. So e to the log base e of x will cancel, and you just get x. Okay, so the answer, the exact answer is e to the 105.78 over 12.44, all that in the exponent. And I think that comes out to be something like 4,000 hours. Let's see. Second, e to the power, make sure you put the power in parentheses, 105.78 divided by 12.44. Oh, close to 5,000. So it's about 4,931 hours, if I round to the nearest hour. But that is how many days? 205 days. I hope that this is not still going on. "205 days from now," but you never know. I'm getting sick of my own cooking. I want to be able to go out to eat. All right, the last thing I want to mention here is just what is the general graph of a logarithmic function? Well, it depends on, so let's let y equal log base a of x. It depends on whether a is greater than 1 or between 0 and 1, just like an exponential function. So the graph of a logarithm is the same as the graph of its corresponding exponential, except you switch all the ordered pairs. So all the x's become y's and all the y's become x's. And so that means although the graph of an exponential has a horizontal asymptote, y equals 0, the graph of a logarithm has a vertical asymptote, x equals 0. No matter what, right? No matter in either case. But this tells us then what the domain and range is for a logarithm. So the domain are all positive numbers. The range is all numbers altogether, right? Definitely goes, those arrows are meant to say that it goes up to infinity and then down to infinity, but doesn't cross that vertical asymptote line. Increasing and decreasing. So if the base is greater than 1, then the graph is increasing all the time. If the base is between 0 and 1, then the graph is decreasing all the time. And as I mentioned, the change of base formula, this is the general formula for it, but we really are only going to use this thing to change from log base whatever to log base e or log base 10. But you can do it for any a and b, right, where b is some other base. So for instance, I wanted to do the log base 3 of 57, okay? That's going to be, if you want, log 57 over log 3. So here, log base 10, 57, divided by log 3, it's about 3.68. Okay, so you'll be asked to do that a couple times maybe in your homework. And that's all I'm going to do for today. Okay? Happy hunting. Bye-bye.